Hi everyone, my name is Bowen Liu. I'm a PhD candidate at the University of Leeds. Today, my presentation is on three-dimensional response of full-scale masonry arc bridge. So masonry arc bridge continue to form a significant part of the transport networks of the UK. There are approximately over 40,000 bridge spans in masonry construction. After being used for over 100 years maybe, their structure and material have been degraded significantly under effects such as weathering, increasing traffic load, and extreme events such as flood under climate change. So replacing all of these bridges can be extremely expensive. In order to make this old bridge keep functional, we need a better understanding on their behavior and damage accumulation to inform their repair strategies. Extensive studies has been carried out to investigate the failure mechanism of masonry arches and arc bridges, from testing small-scale specimens to full-scale specimens. Most of these studies have been performed under planetary conditions, focusing on the two-dimensional behavior of the bridge. However, the real masonry arc bridge always have a strict 3D response, especially under eccentric patch loads. And the interaction between different components can significantly affect their failure mode. There is very limited data available to validate these high fidelity numerical models. So this is the main motivation of this study. So in order to accommodate the bridge, we first built the RC test bed and stiff end walls. We also have an independent reaction frame for the load application. The masonry arc bridge model was designed based on the typical masonry arc bridge found in the UK. It contains English-bound spandrel walls. It contains abutments, a 3-meter span arc barrel, and crushed limestone as backfill. It was constructed by using Type A engineering solid bricks, bonding with lime mortar to reproduce the low bonding strength characteristics found in the real masonry arc bridge. So here is the construction process. For the complete model, we scanned the model and developed this photogrammetry model containing all the details of the bridge. We would like to comprehensively capture the 3D response of the bridge. So we adopt different types of sensors, including potentiometers, LVDTs. We have 2 pairs of cameras as DIC to capture the deformation of south side spandrel wall. We have 4 accelerometers on the top of the wall to capture the ambient vibration response. And before and after the load tests, we did a ground penetrating radar surveys to inspect the inner structure of the bridge. When we adopt loading protocol, we actually have 2 principles. We would like to observe the both 3D response and accumulation of damage. So we applied patch loads at 9 locations on the backfill surface, including centric locations and centric location. So static load was applied under 4 loading levels. We start from mid-level, a low-level load with a magnitude of 150 kilonewton, which is around 20% to 25% of the load carrying capacity of the bridge. And this low-level load was applied to all of these 9 locations sequentially. And then we increased load to mid-level and applied load to all of these 9 locations. For the high level and failure level load, they were only applied to a point B and a point H at the central line over the quarter span or 3/4 span of the arc barrel. So next I would present some key findings of the experimental study. So during the low-level loading test, we observed the early stage damage. When we apply load at point D and point F at the central line, over the arc coin close to spandrel walls, we found these highline cracks occurred between arc barrel and spandrel wall. So if we check the load deflection curve, we can see a clearly change in the slope when load approached to around 60 kilonewton. Further application of the load close to spandrel walls would result in this crack propagated. And then move to the next mid-level loading test. We found when we apply load at 4 corner locations, point A, C, G, and I, we found the opening of tensile cracks at arc introdos under loading location. So this is actually a sign of the formation of the first hinge. And also diagonal cracks occurred in spandrel walls. Loading at other location can potentially result in the localized failure of the motor joints in arc introdos. We apply the high-level load with the magnitude of 560 kilonewton at point B at the central line of the bridge over the quarter span of the arc. So during this high-level loading test, we found the formation of 3 hinges. The first hinge is under loading location. The second hinge is at the loading site close to the spring-in. And the third hinge is at mid-span region where we found the crashing of motor joint during the loading test. So with the increasing of the arc barrel, deformation of the arc barrel, we found the propagate of this diagonal crack in spandrel walls. In addition to the global failure signs, we also observed the sign of 3D response. We found the diagonal cracks in arc introdos originate from the loading area. At the same location, we performed the first failure level loading test. So with the load increase from high level to failure level, we found a further development of these 3 hinges. If you check the video, this video showing the opening of crack of the first hinge, and also you can see the cracks on spandrel wall and between the arc barrel and spandrel wall. The formation of the last hinge, this is at the non-loading side spring-in. And also the 3 main cracks occurred in spandrel walls, which separate the wall into 4 parts. This markable extension of diagonal tensile cracks in arc introdos is actually evidence that the arc barrel behaved in the 3-dimensional way under patch load. Then we move the loading location from point B to point H over the 3/4 span location of the arc barrel. So we would like to access the residual capacity and residual stiffness of the bridge. So from the second failure level load test, we observe the similar behavior of the bridge as the first failure level test. And also the bridge behaved in a 4-hinge mechanism, and the crack pattern is almost like mirrored. So this video showing the north side view of the bridge. Besides the crack mentioned before, we also observed a diagonal crack open on the backfill surface. So the crack starts from the loading platen and propagate diagonally, open when the load approached to its peak value. So we noted these cracks in our photogrammetry model for better comparison. And if we compare the 2 failure level tests, we can see the capacity of the bridge decreased slightly by only 10% from 639 kilonewton to 575 kilonewton. But the stiffness of bridge decreased significantly by 35%. Along with the loading test, we also performed the ambient vibration test to capture the model parameters, the frequency and damping ratio of the bridge. So we established this correlation between the stiffness degradation and the variations in the first order frequency of the bridge. So from the first order frequency, we successfully captured the initiation of early stage crack, the first hinge, and the activation of 4-hinge mechanism. So compared with the undamaged bridge, the stiffness of the fault bridge decreased by 85%, and the first order frequency decreased by 25%. So last part is conclusion. So in this study, we developed a new full-scale testing platform for masonry arc bridges, and we constructed 3-meter span brickwork arc bridges. It was extensively instrumented, and then it was subject to a wide range of load tests from undamaged state to collapse. Besides the data we obtained from the bridge, we also did a series of small-scale tests to characterize the material properties of masonry units, motor joints, and their interface. So all of this data can support the future development of high-fidelity numerical models. So thank you for listening.